This video will cover the lipids section of subtopic 2.3. Here are a list of understandings, application, and skills that will be covered in this video. So we'll start with a review of the basic structure of fatty acids. So fatty acids are basically a chain of carbon atoms linked by a covalent bond. So between all of those carbon atoms in that chain are covalent bonds. And at one end, you'll find a carboxyl group, outlined here. So fatty acids can be categorized as saturated or unsaturated fatty acids. So if there are only single bonds between the carbon atoms, then that molecule gets classified as a saturated fatty acid. And we say it's saturated because if there are only single bonds between the carbon atoms, then each carbon atom is bonded to as many hydrogen atoms as possible. So it has the maximum number of hydrogens attached. So this carbon here, for example, can have a maximum of 2 hydrogens, which it does. So we can't fit any more hydrogens on, so we say that carbon is saturated. Or we can say these carbons are saturated. So our saturated fatty acids have single bonds between each carbon atom. We can have situations now where we have unsaturated fatty acids, meaning that there's a presence of one or more double bonds between the carbon atoms. So the carbons are not bonded to the maximum number of hydrogen atoms possible. So the difference between saturated and unsaturated fatty acids basically refers to the structure of the hydrocarbon chain. Unsaturated fatty acids can be classified as monounsaturated, meaning there is only one double bond present in the hydrocarbon chain, or they can be polyunsaturated, meaning that there is more than one double bond present. So the following diagram shows a monounsaturated fatty acid. So here we have the presence of a double bond between those 2 carbon atoms, and each carbon is only bonded to 1 hydrogen. In the polyunsaturated fat, we have more than 1 double bond present in that hydrocarbon chain. Now, the presence of that double bond can have an effect on the physical properties of the molecule. And this really depends on the orientation of those hydrogen atoms. So those hydrogen atoms can have different orientations, leading to the creation of isomers. And so what are isomers? Well, isomers are molecules with the same number and same type of atoms, but with a different arrangement of those atoms. So if we look at these 2 molecules here, they have the same number of carbon atoms, they have the same number of hydrogen atoms, and oxygen atoms. So if we were to count them up, we would see that there are equal numbers of carbon, hydrogens, and oxygens. The difference between these 2 molecules is the arrangement of those atoms. And in this case, it is the arrangement of those atoms around that double bond. So in one arrangement, we can see that we have 1 hydrogen atom that is above the double bond and 1 hydrogen atom that is below the hydrogen bond. This creates what is called a trans isomer, or a trans-unsaturated fatty acid. This is where we have hydrogens on opposite sides of the double bond. Now, if our hydrogens are located on the same side of the double bond, this gets referred to as a cis isomer. And for cis isomers, the hydrogens can both be above or both be below the double bond. And so the presence of that double bond can affect the shape of the molecule. And the type of isomer present will affect ultimately the shape as well. So with that cis isomer present, or with that cis bond present, and this is where the hydrogens are going to be on the same side of the double bond, This creates a bend or a kink in that hydrocarbon chain. And that bend is permanent. It doesn't straighten out, it just stays bent. Whereas in a trans isomer, where those hydrogens are located on opposite sides of the double bond, this keeps the hydrocarbon chain straight. And so this difference between the straight and bent will affect the physical properties of the molecule. And so how it affects the physical properties is that if we have our trans isomer, for example, where we have that nice straight chain, this can allow the molecules to closely pack together, or closely associate with each other. And because they are closely packed or closely associated, these will have a higher melting point, or a high melting point, that will allow them to be solid at room temperature. Whereas with the cis isomer, where the hydrogens are on the same side of the double bond, it will create that bend in that hydrocarbon chain and will cause, or could cause that hydrocarbon chain not to be closely packed together. So that loose packing of those hydrocarbon chains causes these types of molecules to have a low melting point. And as a result, they tend to be liquid at room temperature. So the following chart just summarizes these properties and characteristics of cis and trans isomers. So it just describes the fact that you have in the trans isomers the hydrogens on the opposite side of the two carbon atoms, whereas in the cis isomer they are on the same side. Cis isomers tend to be very common in nature. You find them a lot in nuts, in plants, and in fish oils. Whereas trans isomers tend to be rare in nature. We commonly find them in artificially produced products such as margarine. So the cis isomer, the presence of that cis isomer causes a bend in that fatty acid chain, whereas the trans isomer does not cause a bend. It keeps it relatively straight. So the trans isomer will be more closely packed, and because they are more closely packed, they tend to be solid at room temperature. Whereas the cis isomer, they will only be loosely packed, and because of that, they tend to be liquid at room temperature. So with those fatty acids in the body, they get stored in the form of triglycerides. So triglycerides are formed by condensation reactions, and just recall that condensation reactions will create water as a product. And so triglycerides are formed from 3 fatty acids and 1 glycerol molecule. So what is glycerol? So glycerol is a 3-carbon molecule. Each carbon is bonded to a hydroxyl group. The hydroxyl group on the glycerol is capable of reacting with the carboxyl group on that fatty acid chain. So in this case, you'll get the hydroxyl from the carboxyl group being removed, the hydrogen from the hydroxyl group of glycerol being removed. Together, these will form water. And then the remaining parts of glycerol and the fatty acid chain will link together. And so because there are 3 hydroxyls on glycerol, this reaction can occur 3 times, attaching 3 fatty acid chains to that glycerol molecule, creating triglyceride. And because you have 3 condensation reactions occurring, you generate 3 molecules of water for every 1 triglyceride that is formed. So triglycerides are the form in which fatty acids are stored in the body, and the body stores these triglycerides as a form of energy storage. So just kind of bigger picture here. So the molecules that are stored by humans and other organisms to be used in ATP production include things like glycogen and triglyceride fats. In times when you do not have access to food, your body needs to store molecules that can be used in ATP production, which is primarily going to be glucose, but it needs other forms of molecules as well that can be used. And so glycogen is kind of the main storage for glucose. So remember, glycogen is that highly branched chain of glucose. So it's all those glucose molecules linked together in those highly branched chains. This is stored in the liver and muscle tissue. This is the go-to for your body to use to keep production of ATP rolling along. When glycogen stores get depleted, your body will need to dip into its long-term energy reserves. So that's where the triglyceride fats come into play. The triglyceride fats are stored within the adipose cells. And triglyceride lipids, when needed, can be hydrolyzed into 2 carbon segments that can be entered into cellular respiration. So if we have our triglyceride here, what this means is that when glycogen stores have been depleted and your body is in need of producing ATP, it can now tap into those triglycerides to create ATP. And it will cleave off these 2 carbon segments from the hydrocarbon chain, which can then be used in cellular respiration. And obviously these will be used at a different starting point from that of glucose. So as long-term storage, lipids are much better for the purposes of long-term storage in humans than carbohydrates. So a gram of fat will store more than twice as much energy as a gram of polysaccharides. And keep in mind that we do move around a lot. We're not in one place for most of the time. So we have to be able to carry our energy stores with us. So it's more advantageous to have a more compact reservoir of fuel. So the fact that we can more efficiently store energy in the form of fat as opposed to carbohydrates. And so another advantage is that that fat is stored in adipose cells, and those adipose cells form adipose tissue. And that adipose tissue can serve some functions. So it can serve as a cushion for vital organs, such as the kidney. Adipose tissue can also be found beneath the skin, which also serves as a layer of insulation to help keep us warm. And the other advantage of using lipids as long-term energy storage is that lipids are insoluble in water, so they will be stored outside of the cytoplasm of these adipose cells. So these triglycerides or these lipids will not affect the osmotic balance of the cytoplasm of these adipose cells. Whereas storing glucose in the form of glycogen would be stored directly within the cytoplasm itself and could affect the osmotic balance of the cytoplasm of a cell. So part of what you'll be able to expect it to be able to do is to calculate body mass index or BMI. So consuming too much of anything can result in gaining excess weight or storage of excess fat, and this can lead to a number of health problems. So a number of screening tools have been created to help identify potential situations that could result in various diseases. One of these tools is the body mass index, or BMI. So it is a screening tool to identify potential health problems, but other factors such as diet, physical activity, and family history have to be assessed in order to get a proper picture of one's health. So BMI is a score that ranges anywhere from, say, about like 15 to about 40. That's kind of the typical range. You can get lower scores or higher scores, but this is the typical range in which BMI scores will be found. A BMI score basically takes into account the mass of the individual by the height of that person. So to calculate BMI, you take the mass of the person in kilograms divided by the height of the person in meters, and that is squared. And you get units of kilograms per meters squared. Now, because a lot of us still refer to our height in terms of feet and inches, conversions are provided for converting meter height into inches. And because we generally refer to our weight in pounds still instead of kilograms, the conversion for converting your mass, your mass in pounds to that of kilograms. And so when you calculate the BMI, you get a score, like I said, somewhere, ideally, somewhere in this range of 15 to 40. And the number that is generated, can be used, can be used to identify a category, identifying the person as either normal weight, underweight, or overweight. So typically, BMI scores of 18.5 to 25 are considered normal. Anything below 18.5 is considered underweight. And then a BMI score of 25 or greater, or higher than 25, that person would be considered overweight. And then obviously the higher up you go, you enter into that, into those categories of being obese. And so there are some dangers of using BMI. Like BMI is just one tool, but it's not always the most accurate because it's only taking into account your mass in kilograms. It doesn't take into account what percentage of your body is muscle versus fat. So you could have a very muscular person that has a high BMI score. Basketball players are the classic example of this, where they are very muscular individuals, and they can be tall, but they are very muscular individuals. And when their BMI scores are calculated, they tend to be into the overweight to obese scores, but they are very physically fit individuals. So that is one of the problems with calculating a BMI or just using BMI alone to assess the health of an individual. There are different ways in which a BMI score can be calculated. One of them is by using a nomogram. A nomogram is basically where you have one set of measurements on one side, another set of measurements on the other side, and then in the middle is what you're trying to calculate. So in this case, BMI. So the way this works is that you use a ruler to draw a line from the body mass to the height. So if we have a body mass of, we'll say, 65 kilograms and a height of 175 centimeters, if we draw a line connecting those two, and I'll try to draw the straightest line I can possible. It's not a straight line. It serves the purpose to illustrate what we're trying to do here. Where that line intersects the weight per height squared line, so where it intersects that middle line, is the BMI score. So in this case, we would have a BMI score of 22, and this person would be considered in that healthy weight range. So one of the things you'd be expected to do is to assess the scientific evidence for health risks of trans fats and saturated fatty acids. So this slide will just kind of walk you through the comparison of the main types of fatty acids. So as mentioned at the beginning of the video, we have those unsaturated fatty acids, saturated fatty acids, and trans fats. So with unsaturated fatty acids, those examples where you find those include things like almonds and vegetables and fish and olive oils, for example. And the health effects there is that, it raises what is considered good cholesterol levels, whereas things like saturated fats and trans fats tend to raise those bad cholesterol levels. And so those saturated fats tend to be found in things like beef and butter, dairy products, pizza, in the form of cheese. Trans fats tend to be found in processed foods or heavily processed foods, so things like fries and cakes and donuts and cookies, all those good foods, have those trans fats which raise those bad cholesterol levels. And so in class, we will go through some evidence and the methods used to obtain the evidence for health claims made about lipids, and this will tie into that nature of science statement as well. So this does it for this video about lipids in subtopic 2.3.